know which one you all think is the best medium after class, whether the Skype call is beneficial for the interactivity, or whether you prefer the videos or some other class medium, right? So yeah, I think some people still having problems joining it. Okay. Right. So as I was saying, in the last 4 videos, we basically wrapped up section 1. So we went through. Good. Right, nice. Thank you. So once you can see the screen, this is all I'm going to be using for this class. So the screen and my voice is basically all I need. I can disable the video if we need to. Right. So in the last four classes also, we got all of this covered in class. I think up to 1.5, 1.4, 1.5, somewhere there. We had covered the first section in class, and then after that we transitioned to the videos, and we covered up to 1.13 in the videos. So let me know if you don't have access to those videos. They are on my YouTube channel. I made them public, so it'll be easier to find them, but the links are also in the chat. And as I was saying before, I may have missed stuff in the video. I may have gone through things too fast. Subnetting especially is a heavy topic. So if there's anything in the video you want to ask questions of, anything in the lab you want to ask questions on, hit my message on WhatsApp, and I will legit have a one-on-one call with you in Skype or Zoom or anything you want. Students have been contacting me, and I have scheduled them whenever they have time and whenever I have time. It's no problem. I'll pull up the presentation and I'll go over it. Any questions you have, you can share your screen, and I'll explain as well. So let me know. Take a look at the videos, and then get the basis there. And any questions you have, take a note of them, and then give me a call, and we'll go through anything else, right? Right. So for this class, we're gonna start section 2.0. So as I mentioned, section 1.0 is the basis for everything. Is a lot of describing and a lot of basic configurations. So basically, up to this point, you're supposed to feel kind of like a network engineer. So you went from knowing theoretically nothing about networks to, if somebody asks you what a router is now, you could at least tell them it does this and this. If they ask you what's the difference between a router and a switch, you know kind of what a switch does, you know kind of what a router does. And you know, if Cisco asks you what is a 2-tier model and what a 3-tier model is, you can describe all of these things to them. You have a rough idea of it in your head. And some of these things, honestly, you just need to kind of stuff in your head, like what is a global unicast address, and what is the prefix, the special prefix that it starts with. So yeah, just reread those things and try to memorize those special prefixes and those special IP address ranges as much as you could. And for subnetting, of course, that's the one big thing you need to practice. I don't think me explaining it is going to help as much as you practice, which is why I gave it the practice website there. So yeah, for everything else, I would say reread and go to the textbook, but for subnetting, practice. Right, so in the last class, what we ended off with, so virtualization is kind of just an explanation. So you see Cisco just said explain the concepts there. So you just need to understand the raw, well, the base definitions of virtualization. So what is a VM, and what is a hypervisor, those kind of things. But the more important thing I wanted to focus on for last class into this class was the description of switching concepts. So you remember, let me pull up a quick diagram here. 1 second. So that was all virtualization. Right. So let's present on this quick. Right. So hopefully you all still seeing this here. So remember, I went through this example here, where I said we had these 3 hosts with 3 separate MAC addresses, of course, and they all were transmitting 1 frame at a time, just so that we could take it slow and understand how the switch forwarded these frames. And we went through where this frame would go. So yeah, we went through this source address and this destination address, and how the switch would broadcast this frame out because it doesn't know where to send it, but it is going to populate that table, and it's going to wait for a response. And then when the response comes in, it's going to use that entry that it has to send it back to A alone, and is also going to populate again with that B source address. And then eventually a frame will come to C, and it's going to use, well, first it's going to broadcast the frame because it doesn't know where C is, so this is all it knows about. But eventually when C responds, it's going to look at that source address and populate another row. So eventually it will learn all of this information about all of these hosts that are connected to it, using that source MAC address in every Ethernet frame. So I hope you all watched that video, and you could follow along with this process. If you're lost on it, give the video another watch or give me a call, and I'll go through this whole process and I'll take it very slow and step by step. And the reason I especially want to make sure you understand this is because today we're going to be expanding on this, right? So this was the basic operation of a switch. So this is how switches are better than hubs. They use these bits of information in their MAC address table to make intelligent forwarding decisions. But all of this is one flat switching network. In today's class, we're going to talk about these things called VLANs, which add another bit of information into that special Ethernet header. Right? So yeah, we mentioned the whole process of switching and ASICs, and the whole point of ASICs and the whole point of this switching process was to make our networks more efficient and more intelligent, which is how we could get our very fast switches these days, which was like up to 400 gigs. 400 gigs, I believe, is the latest, well, the fastest switches that we have nowadays. Right? So, right, there's the other important point I want to make. I believe last class may have been one of the first times we really spoke on commands. So usually it was that I showed descriptions and definitions in class, and then in the lab is when you would run the commands and when you would see the output and stuff. So in this class we're going to change that up a little bit, because in the topics here, the topics for this class, you'll notice that Cisco just wants us to configure stuff. They don't really care for definitions and stuff anymore. They want us to go a step above that now and learn much more configuration commands. So you'll see this command like show MAC address table. I'm going to show you the output straight in the class. Wait, let me make sure. Okay. Right. Okay, good. I just wanted to make sure people just not mass complaining on the group while I'm teaching. Okay, so you all should still be good. Yeah, so we're going to show the command you're going to run. So I'll try to put it in bold or italics so you'll know it's a command you could enter in a Cisco device. And I'm going to show you the output one time in the class. Yeah, because this is really what Cisco wants to learn. Right, so let's start on the base description there. I can close this for now. Right, so that's what we covered last class: switching concepts, MAC learning and aging, frame switching, frame flooding, and then the MAC address table. So at least it not sound like Spanish anymore in your head, I hope. When I say a MAC address table and when I say frame switching, that diagram that I just showed you, I hope it coming in your head, and the concepts kind of popping in for now. So don't worry about being a master of switching yet. I just want you to have the concept, the fundamentals in your head. Right, so in this class, we're going to cover 2.1 to 2.4. So all of this. Don't worry, it is not that much because everything is configure and verify. So see, configure and verify VLANs, inter-switch connectivity, layer 2 discovery protocols, and then layer 2 and layer 3 Etherchannel. So rather than spending a lot of time, with diagrams and descriptions and all of these things, a lot of these later sections are going to be just configurations and learning how to apply the thing in real life one time without, understanding how to define a VLAN and all of these things. We're just going to show you how to do it on a Cisco device one time. Right, so let's get started. Right, so 2.1, the start of section 2. So reach here. So configuring VLANs. When we introduce switches, we said that they were created to extend LANs or layer 2 networks. So LANs, of course, were local area networks, right? When somebody says a network or office network or anything, it's a LAN or a layer 2 network. Switches massively improved networks by segmenting collision domains, since each switch port is its own collision domain, meaning that hosts on each switch port can transmit simultaneously. So we went through that in last week, I believe, last week and the week before. We went through that whole thing about hubs and how if we have two hosts transmitting at the exact same time, their frames are going to collide on the wire. And then Ethernet is built to handle this by telling them, no, you can't transmit at the same time. Back off for some random time and then try again. And eventually, both hosts will get to transmit using that kind of back off the random time. And that's going to tell them, you wait for 6 seconds, you wait for 3 seconds, and they will eventually get to transmit. But of course, that takes a lot of time and it reduces the efficiency of the network a lot. So you can see switches massively improve these networks by segmenting those collision domains. So the collision domain, as you can see here, the collision domain is directly between the host and the switch port. That's it. This host doesn't share a collision domain with this host anymore. However, by default, hosts connected to a switch or a set of interconnected switches are all in the same broadcast domain. So you see it here? They're all in their own collision domain. So that's the purple circles here. Collision domain, and hubs extends collision domains if you have a hub. But they're all in the same broadcast domain. They're all in this kind of off-green square here. Having too many hosts in the same broadcast domain increases the risk for broadcast storms, which are massive amounts of broadcast traffic on the network. And it also decreases security, since any host on the network can listen to the broadcasts. Yeah, so you could kind of see why big broadcast domains are bad, right? Because if people start broadcasting data all over the network just gonna stop and it's gonna slow to a crawl basically. And this is a problem in a lot of current and old networks. I would say a lot of networks still have it. If you have one switch that has a loop or something that's creating a broadcast storm, all of your legitimate traffic could just get sidelined. It can't be transmitted because all the switches transmitting are these broadcasts. That's it, nothing else. Now, routers can be used to separate these broadcast domains or layer 2 networks or LANs, but routers are often expensive and their ports are often limited. So, as I said before, routers are super expensive and they could process a lot of data and run a lot of complex routing protocols, but they don't come with a lot of ports. If a switch comes with 24 or 48 ports, that's normal, but routers will often come with like 4 or 8 ports for the most. Now, another way to segment broadcast domains is by the use of virtual local area networks, or VLAN segmentation. So you see, rather than using a router every time we want to split a network, we're going to use these special things called VLANs to separate our network. This segmentation also helps to better manage and track hosts across our enterprise. So remember, the big thing we were trying to solve here is these broadcast storms, right? The more we segment our network, is the lower the chance we have that somebody going to broadcast a set of data and bring our whole network to a halt. If we have, let's say, 4 hosts in a VLAN now, only those 4 hosts are going to slow to a crawl when somebody starts transmitting a ton of broadcasts, rather than the whole 100 or 200 hosts we have on our network. Yeah? Hit my message in the chat, in the Skype chat, if you have any questions. I'll keep an eye on it as we go along, because I can't really see hands here. So yeah, hit my message if you have any questions. Right, so before VLANs, of course, everybody was in the same broadcast domain, right? Now, after VLANs, so this is what VLANs let us do, is we have one big switch here, and then you have a switch on each floor, which is very realistic, right? If you're on a floor, you want to have a switch right there to connect to. And then if you have hosts, let me say this guy is in sales, this girl on 2nd floor is also in sales, and then this other girl on 3rd floor is in sales, they could all be on the same VLAN, and they should be, right? If they're all in sales, then they're all on the same team, and they all need to share the same resources, and they should have similar IP addresses, and all of that jazz, so we could keep track of them, right? It makes sense in your head that everybody on sales should be on the same network. Same way everybody in HR, same way everybody in engineering. So VLANs give us this power now to say, even though you're on a separate floor, you could connect into the same network as this guy on this other floor, as this guy on this other floor, because you're going to be on the same VLAN. Yeah. So a VLAN is of course a broadcast domain and is also a logical network or a subnet. So that's the two big advantages there of VLANs. It helps us separate broadcast domains and it helps us logically divide our network. So rather than having, you remember when I said the whole 10.0.0.0/8 network was this giant network that we could use for private addresses, rather than using that giant network and making one big network for our business out of that, we could now say, okay, only 10.0.0/24. Only that small /24 is going to be for sales. Then we're going to segment it and make another /24. So we're going to subnet again, get another subnet, and put HR into that subnet. Then another subnet, put engineering into that subnet. So we now segment those broadcast domains and make a lot of mini networks instead of this giant network, which helps us with this broadcast storms and everything. Yeah? So VLANs allow us to create logically separate networks using the same physical switch. So you don't need a new switch every time you want a VLAN or anything. You have this one switch here, and you can have port 1 in VLAN 1 for management, port 2 in VLAN 2 for PCs, for instance, port 3 in VLAN 3 for VoIP, and port 4 in VLAN 4 for cameras. And you can see all of them have their own networks here. So 10.whatever.1.0, .2.0, .3.0, and .4.0. So those are 4 different subnets, so 4 different networks. And each one is associated with something. And this is how we do networks in real life, right? When we hear a network, we know, okay, you're talking about something. If you see a broadcast from an IP, you know it is something. So for instance, if you see a bunch of flood, you see a flood of traffic on your network, on your firewall or something that picks up a flood, you could look at a source IP and you could say, okay, that IP is in the camera network. It is 10.something.4.100. Therefore, I know it has to be a camera. And therefore, you could go and watch all the cameras and see if somebody replaced one of the cameras or one of the cameras given trouble, or something like that. As opposed to if you had all of them on the same network, it would be a lot more difficult to troubleshoot and trace down that bad device. Yeah. And again, all of this could be done on a single switch. You don't need to put 4 switches in an office or in a floor to have 4 VLANs. You could do 4 VLANs on the same switch. So VLANs allow us to save on cabling and infrastructure costs while being able to segment our network by port. They work by adding in a 4-byte tag into the Ethernet header. And this 4-byte tag is called the 802.1q tag. So 802.1q, whenever you hear anybody talk about this is the protocol for VLANs. This is what everybody uses to put that special VLAN tag into there. So we had the destination address, we had the source address, we had the type, we had the data, we had the frame check. We had all of this before in a normal Ethernet frame. And now we're going to insert this special 4-byte header, well, 4-byte tag into this header. So we're going to kind of extend out our Ethernet header. And we're going to use this to put our VLAN ID. So we have a bit of other information in here, but what we care about mainly is our VLAN ID. So you're going to see how we use these VLAN IDs, or how we create these VLANs, and how we put hosts into VLANs on Cisco switches. So we generally configure VLANs by creating VLAN access ports facing our end devices. So the end devices are the phones, the PCs, whatever it is. So we create access ports for those devices, and then we use VLAN trunk ports facing other VLAN-enabled switches. So you see here, there's the diagram here. We have 3 switches. So let's say 3 Cisco switches. We have these things as trunk ports between the switches. So one trunk port and an next trunk port there. And then facing the end hosts, we have access ports. So these access ports connect to the end devices. So PCs. So you have PCs here. And in this case, the colors represent VLANs. So in the well, as you'll see, when we go into the switches, the VLANs are represented by numbers and names, but they use colors here to help you see it easier. So you can say this blue might be VLAN 2, green might be VLAN 3, brown might be VLAN 4, just as an example. And the trunk ports could carry all of those VLANs or one VLAN, depending on what we want. In this case, we only have hosts in this blue VLAN here, so we only carry in traffic for that. In this case, we have hosts on all 3 VLANs, so we carry traffic for all of them. However, access ports could only carry 1 VLAN, so you can't have a trunk port going to here, or you shouldn't. So I'm going to show you how to configure these access ports and how to configure these trunk ports now. So access ports are configured for one or possibly two VLANs. So we're gonna talk about this thing in brackets here. While trunk ports carry multiple or possibly all VLANs configured on the switch. So when people talk about trunks versus access ports, just think access port, usually one VLAN, trunk ports, usually a bunch of different VLANs. So to begin VLAN configuration, we must first create the VLAN on the switch and give it a name. This is a very important step, as Cisco switches do not forward traffic for VLANs that have not been created on them. So basically, if you want to use VLAN 5 on a switch, you want to connect a PC to VLAN 5 on a switch, the very first thing to do is create VLAN 5 on the switch. If you don't create VLAN 5, that switch could never forward traffic on VLAN 5. And this is important even for transit switches, right? So if you have, let's say, two switches stacked and you connect in trunks through them, and you connect in hosts. Let's say you have VLAN 4 and you connect in VLAN 4 on the two edge switches. You want to configure VLAN 4 on the middle switch as well, because if you don't configure VLAN 4 on that middle switch, it will never forward traffic for VLAN 4. It will be dropped as soon as it sees it. And this is a very common problem in networks when you have tens or hundreds of switches. If you have just one switch that doesn't have the VLAN configured, then that switch will drop the VLAN traffic. So it's a very common problem that you just forget to configure the VLAN on one switch, and then the other switches can't ping each other, or the VLAN traffic can't flow through the network because that one switch doesn't have the VLAN configuration. So what's the actual VLAN configuration? So all you do is go config T and then VLAN and the VLAN ID. So that VLAN ID is a number, and then after you press enter there, you put name and your VLAN name. So look at it. So switch config. So remember, if you see this config in brackets, it means that somebody put config T and typed enter already, and they reach for this config here and the pound sign, of course. So all you're doing is you're typing the word VLAN space and the VLAN number, and you press enter, and then you see it moves to config VLAN. So we're in the VLAN sub configuration menu now, and we're going to configure things for that particular VLAN. So we put name space and the name of the VLAN. So you see black hole here and desktop PCs here. So this just means that we name in VLAN 99 black hole. So just as a background here, not that important, but usually when you configure in VLANs, people want to configure a black hole VLAN. So it's for security, right? If you have a switch that's in your office or facing a customer, in your payment center or something, you don't want people to be able to come and plug into that switch and be able to access anything on your network, right? That's a huge security risk. So what people usually do is all the ports that they're not using, or all the ports that might be, a customer might be able to plug into, they put it on a dead-end VLAN or a black hole VLAN. And in this case, that's VLAN 99. And then anybody who plugs into this can't access anything. It's just a dead end. The network doesn't actually connect anywhere, or that VLAN doesn't actually connect anywhere. Yeah, so that's 99. And then in this case, 101 was desktop PCs. So they put VLAN 101. So they let this switch understand VLAN 101, and they assigned it a name, desktop PCs. So this isn't fixed, so don't memorize this by any chance. All you need to memorize is the command, VLAN, and then VLAN ID, and then name and the VLAN name, because this could change. So you could have a network where 101 is desktop PCs, and the next network, 101 might be some special corporate customer. It might be Wi-Fi, it might be just one link to an access point, it might be anything. So there is no mapping between VLANs and names. You assign the name in your network. The important thing is the ID. Right, so once you've configured the VLANs in your networks and their names, you could verify the VLAN configuration with the show VLAN brief command. So you see this type, you see the no config here, so we're not in configuration mode. They exited out of that. We back into just the show mode. They do show VLAN brief, and you can see a listing of all the VLAN IDs that we have created on our switch and all the names of those VLAN IDs. So in your lab, or if you're doing random tests, you might see these names might not be here because it'll just be named VLAN 101 by default. And VLAN 101 doesn't make a lot of sense to us, right? If we see VLAN 101 and VLAN 102, we don't really know what's in those VLANs, which is why we give them names. So the names aren't mandatory, but the names help us know what the VLANs are used for, right? So if we created VLAN 101 and we give it a name desktop PCs, and then a year down the road, we want to add a new desktop PC into our VLAN, we could come back and run show VLAN brief, and then we know, okay, this VLAN 101 was desktop PCs. So you know one time which VLAN you need to put in to connect a desktop PC. Right? So that's the whole point of names. It's just to make it more readable and more understandable for us as network engineers. So show VLAN brief, and you'll see this whole breakdown of the VLAN IDs, the VLAN names, and which ports are assigned in which VLANs. Now, after we configure our access ports, so you see we have no access ports configured into these VLANs yet, but we did create them. All the access ports are in VLAN 1 by default, which is why you're seeing all of these here. So after we configure our access port, this is just the next example. We can then configure our interface or interface range to become access ports in a particular VLAN using the command switchport mode access and switchport access VLAN something. So you see here, all we did was configure the VLAN. We didn't put it into our access port yet. We just created it on the switch. So after we create it on the switch, we go in and we could put certain ports into those VLANs. So we get them out of this default VLAN 1 into these special VLANs we create. So we go into interface, and then we use the command switchport mode access and switchport access VLAN something. So VLAN 101, VLAN 102, VLAN 201, VLAN 301, whichever one we want to configure. So you see VLAN 10, name engineering. So we know how to do that already. This was just creating the VLAN. Then from config mode now, we go interface fast Ethernet 01. So we go in under our particular interface. And then once we go in there, you see it changed to config IF. So it's in the interface configuration mode now. We go switchport mode access. And then switchport access VLAN 10. So we're saying this port is now going to be an access port. So we specify that it has to be an access port. It will never be a trunk port. And then we go switchport access VLAN 10. So you are going to be an access port in VLAN 10. Now, I believe I showed some of you the interface range command before as well. So rather than doing interface fast Ethernet 01, let me say you wanted to configure 3, 4, and 5 as interfaces in this VLAN as well. You could go interface fast Ethernet 03 and then exit out, and then go 04 and exit out, and then go 05 and exit out. But a faster way is to type in interface range fast Ethernet 03-5. So you're configuring all of these ports as something. So what's that something? We configure switchport mode access. So we configure all of these ports to be access ports, and then switchport access VLAN 10. So we put all of these ports as VLAN 10 one time. Yeah, so it's a little shortcut. Now, in addition to our normal access VLAN, so that's what we did. We created these as access ports and put them in one VLAN. In addition to those normal access VLANs, which I call them data VLANs here, we can also configure a special VLAN called a voice VLAN. So we had that normal access or data VLAN. Now we also have a voice VLAN using the switchport voice VLAN command. So when you do switchport access VLAN command, that's your first VLAN you can put on it. But you also have switchport voice VLAN to configure a second VLAN ID on an access port. So this is a very special case, right? Usually, this is what you're going to configure. You're going to put it in access mode, and you're going to configure a VLAN on the access port. But there are special cases when you want to connect PBX VoIP phones to these ports. And this is how the configuration looks, right? So you have a switch here, and this port connects to the switch. So this is your patch cable here. But this cable is going to connect to the switch, to the VoIP phone, sorry, or the PBX phone. And then in the back of this phone, you'll see there's a port facing the LAN. So that's how we connect to the switch. And there's a port for a PC. So the PC is going to kind of piggyback off this phone. So you can see now this cable here, or this interface here, kind of needs to connect to two VLANs, right? Because we have a phone VLAN, and we also have a VLAN for PCs or desktops. So in this case, we put it as an access port, switchport mode access, but we also put access VLAN 10 to say PC needs to be in VLAN 10, but switchport voice VLAN 20 to say this phone, I want you to be able to go into VLAN 20. So you see this port is an access port, but it now has two VLANs, a 10 and a 20 for that normal access VLAN and that voice VLAN, just for PBX phones. So this doesn't apply to anything else. It's only PBX phones that use this, which is why it's voice VLAN. But your access VLAN could be anything. So you could have PCs, printers, access points, whatever it is. These all use that normal access VLAN and a number here for that VLAN. But the voice VLAN, that is used for this very special case where you have a cable going to a PBX phone and then the back of the phone connects to the PC. And in a lot of offices, you'll see they have a setup like this because they don't want to run two cables from here to here now. A lot of these cables will be pre-terminated in the walls and using crimped connectors and all of these things. So they don't want to go and run a second connection. They just have this one connection from the switch to the phone, and then the PC just connects to the phone there. So because of this, and because Cisco saw it was so important and so prevalent in the industry, they said we're going to create a special voice VLAN command just for this. So it allows the PBX VoIP phones to tag their own VLANs for a PBX network, while still allowing the PCs behind them to tag their VLANs. So memorize these commands. Note that by default, Cisco creates a default VLAN using tag 1, and all switch ports are assigned to this VLAN out of the box. This default VLAN cannot be edited, but Cisco recommends that all ports be configured to a particular black hole VLAN, and that a separate VLAN be used for management. So this default VLAN, everything in your switch is assigned to this VLAN by default. As long as the switch could understand VLANs, if you do a true VLAN on a factory reset switch or a factory defaulted switch, you'll see this default VLAN being created here. And all of these ports, so all the ports on the switch will be in here by default. These VLANs are also created by default, the FDDI and token ring and all of these things. I have never seen these used, so you can read up on them if you want. But really, Cisco just created these for other technologies that were used at the time. And in most of the networks that I've seen, we just don't use these VLAN IDs. They're already created, so they're already in use because they're created by default. So we can't use these IDs again. But we just kind of work around them, right? So you could create 2, 3, 4, 5, all the way up. And then after this, you could go down and create some more. So I'll give you the full ranges in a bit. But by default, this is what's created on the switch. 1, and then these 1002 to 1005. That's the default that's created on the switch. And everything is in VLAN 1 by default. So remember that. Default VLAN, VLAN 1, all ports in it by default. I explained the whole concept of the black hole before. That's just a special VLAN that you want to create just so that if somebody connects into that special VLAN, they won't go anywhere. They won't have access to any of your infrastructure devices or any services or anything. It's just a dead-end VLAN. Now, valid VLAN range is from 1 to 1005, so that's the normal range, and then 1006 to 4094. So you see, we created that kind of bridge there. Very old Cisco switches may only support these normal VLANs, so you won't be able to create anything beyond 1005 in those very old switches. But most of these Cisco switches that I've come across can use the full range, the full extended range. So from 1 to 4094, they could use all of those VLANs. 1 and 1002 to 1005 are created by default. Yeah, just solve it, please. Yeah. Okay, cool. Yeah, so 1 and 1002 to 1005 are created by default. So that's what we just saw. Sorry, here. That's what we just saw here. And 0 and 4095 are reserved. So you see, same thing here. 1 to 1005. Yeah. Cool. So just to re-emphasize, we use VLANs to create separate networks to segment host machines, right? So that was the whole point of that whole thing into VLANs. We wanted to create separate networks to segment our host machines. Now that means that without some form of interconnectivity, hosts on a particular VLAN can only communicate with hosts on the same VLAN, not on other VLANs. So if we created VLAN 2, which was marketing, and then VLAN 3 for accounting, and then VLAN 4 for sales, then by default, so if you have nothing else upstream and nothing else in the core, nothing else, just that switch with those separate VLANs, these hosts can't connect with each other. Remember, because we segmented that network now, right? So by default on a switch, when everything is in VLAN 1, a PC here could ping a PC there, no problem, they're in the same VLAN. But now, with these VLANs being used for segmentation, this PC here can't ping this PC in this other VLAN without some form of connectivity upstream. So that's where the trunk ports and the router on a stick and all of those things come in. But by default, when you separate hosts into their separate VLANs, they can't communicate with each other. So in this case, just with this small network here, you could ping from PC5 to PC6, no problem. If you want to ping from PC5 to PC4, you can't do it right now because they're in separate VLANs. Yeah? So in order to allow communication between hosts on different VLANs, we need to perform some sort of inter-VLAN routing. So we need to route traffic between these different VLANs. Now this can be performed by a layer 3 switch or by a router on a stick. So router on a stick is really a router, and you kind of see in the stick there, it's just a connection. It's just a fancy name. But it could also be done by a layer 3 switch. So there's the concept, right? You have VLAN 10, 20, 30, 55, and 77, all separate VLANs. And by default, none of these hosts can ping each other, right? They're in separate networks. They can't reach each other. Now, this connection up to this router here will be the bridging point. So we're going to set up this special trunk connection here. It will go up to the router, and the router is going to route this traffic between these different networks. So for instance, this host, if it wants to reach this host, the traffic is going to go here, up this trunk port, go to the router, be routed back down here, come here, and then go there, right? So without this router here, this connectivity can't happen. With this router here, a packet could go here, and come back down and go there. Yeah? So you see me stick there, up and then down. Of course, for a router to route traffic from multiple VLANs, a port has to be configured that allows these multiple VLANs to pass. We will explore these trunk ports now. So as I mentioned before, usually when you hear the word access port, you think in one VLAN. So there's that very special case with the PBX phone that allows 2 VLANs, but usually when you think access port, I want you to think one VLAN, as opposed to multiple VLANs, which is trunk ports. So whenever you hear one VLAN, think access ports. Whenever you hear multiple VLANs, think trunk ports. So once we've created access ports for end devices on switches, we then need to create trunk ports to allow multiple tags to other switches and routers. Some older switches allow trunking using a protocol called ISL. This is not used anymore, but on these older switches, we first need to enter the command switchport trunk encapsulation 802.1q before entering the switchport mode trunk command. So remember, we did switchport mode access before. So that whole switchport mode access command was to tell the port you are going to be an access port, right? Now we want to tell a port you are going to be a trunk port. So all we do is switchport mode trunk instead of switchport mode access. But before we could do this, on a lot of the older switches, you need to use this special command. Switchport trunk encapsulation 802.1q. So this just tells the switch you are going to do trunking, and you're going to do that trunking using this special 802.1q protocol. Remember, we mentioned that this is how we do VLANs nowadays. Well, before there was 802.1q, there was another protocol called ISL. So these older switches could do either ISL or 802.1q. So you had to tell it which one you want to do. So this switchport trunk encapsulation 802.1q command was a special command we had to put before we could put this switchport mode trunk command. So in a lot of the older switches, you'll see they still need this. If you try to enter switchport mode trunk before entering this, it will tell you, please put this command, basically. So this is what trunking looks like, right? You have a switch here, you have another switch here. You have VLAN 1, VLAN 2. So this will be on 2 separate access ports, VLAN 1 and VLAN 2 here. And to connect these 2 VLANs, you want to put a trunk port here. So this is one physical cable that's going to carry traffic from multiple VLANs. So that's what a trunk is. So you see the command here, switchboard trunk encap, which is short for encapsulation, and 802.1q or ISL. You have to pick one. And in the modern day switches, we use .1q. So interface is in, I don't know why I say it's 801, it's 802.1q trunking protocol. So switchboard trunk encapsulation .1q. So this command configures VLAN tagging on an interface if the switch supports multiple trunking protocols. The two options are .1q for IEEE 802.1q and ISL. So I've seen the command change on different versions of switches. So usually I would say just put switchboard trunk encapsulation and put a question mark here, just as they did here. Remember, I showed you when you put the question mark, you could see the next command that comes after it, or the next word that comes after it. So it might be .1q, or it might be something a little different. So different versions of switches, I've seen the command changed a little bit. So just use a question mark and figure out the exact command for your version of switch. If you're working on older switches or whatever, if you're working on slightly different switches. Once we've configured our port as an 802.1q trunk, we have a few more commands to add. We can use switchboard trunk allowed VLAN all to allow any tag to pass across the trunk, or use switchboard trunk allowed VLAN 1, 2, 1000, 2000, etc. to only allow particular VLANs. So what we're saying here is, remember, a trunk port is used to pass multiple VLANs across, right? But again, for security reasons or for efficiency reasons, we may want to use some trunks and filter the VLANs that are allowed across them. So for instance, we might only want to allow VLAN 1, VLAN 2, and then VLANs between 1000 and 2000 across them. So we use this special command, switchboard trunk allowed VLAN 1, 2, and then 1000 to 2000. So this filters the VLANs that are allowed across that link now. So for instance, if you try to send VLAN traffic for VLAN 2001 across it, it is going to drop that traffic. It's not going to allow it. If you try to send traffic for VLAN 2, it will allow it because it is in that allowed range. Yeah. If we don't care about security and we just want to keep it simple, just put switchboard trunk allowed VLAN all into it. So this is the default on Cisco switches. If you don't put this command, this is what Cisco will assume, and this is what it will roll with. But I like this IP18 just so that I remember in my head I am allowing all VLANs across this trunk. Whereas I could be more efficient, or I could put more security into my network and only allow certain VLANs across it, depending on your network configuration. So as entry-level network engineers, usually your architect will tell you this. They'll tell you, across this trunk, only allow these VLANs. Or they'll tell you, across this trunk, allow everything. Now, additionally, we should always use the switchboard no negotiate command to disable Cisco's dynamic trunking protocol, or DTP, across the trunk. This protocol is used to allow switches to detect trunks, but it is a security risk. So a long time ago, people used to use dynamic trunking protocols to allow two switches to kind of negotiate a trunk between them. So if you connect one switch to another switch, the switches would try to form this trunk automatically. But obviously, you can see this is a security risk, right? If you leave this DTP on and somebody connects a PC into it and they figure out how this DTP works, they might be able to access traffic from a VLAN that they're not supposed to be able to. For example, if you have VLAN 10 that your CUs connect to, and somebody connects into a port that supports this DTP, and they're able to tell the switch that they want a trunk port, they could pull traffic from this CU network. So you can see why this is a bad risk, right? Well, a risky practice in a network. So usually the best practice is to just disable this DTP. So this is the full command for a trunk now, right? So interface fast Ethernet 5.8 or whatever port you want to configure, shutdown. So usually we want to shut down the port before we make our configs. So switchboard trunk encapsulation .1q, of course. So we want to start off with this to tell the switch which protocol we want to use. Then switchboard trunk allowed VLAN 1, 15, 11, 1002 to 1005. This is optional, and these numbers are random, right? Don't try to memorize these numbers. This will be based on your network and based on the design that your architect gives you. If you're unsure of this, just put switchboard trunk allowed VLAN all and leave it as that. Then switchboard mode trunk. So you put in this port as a trunk port, and then switchboard no negotiate to disable that risky DTP on our network. And then as the very last command, we put no shutdown to bring the port back up. And now this port will have our nice trunk configuration on it. So the port went down before, and we put our new commands, and then we bring it back up. Just because, in the middle here, something might happen, and it might screw up something on the network up the road. So usually you want to shut down the port first, put on all the new commands, and then do a no shut to bring your port back up. Yeah. So then we put our commands here, and we want to verify these commands, right? So we then run a show interface trunk command to verify our VLAN trunks. So you see show interface trunk, not in config mode again, just exit out of config mode and show interface trunk, and you see everything we just configure. So FA01, what mode is on. So when you put switch port mode trunk, you are putting it in mode on. It's telling it you are going to be a trunk port. I'm not giving you an option to negotiate that. You are a trunk. And then encapsulation 802.1q, because we tell it to use this protocol, and then status trunking. And then native VLAN, I can't remember. Right, so yeah, so the next slide will explain this native VLAN bit. But up to now, I hope you could understand the port and the mode and the encapsulation and then the trunking. So the port is the port we started off with here. So 58 or 01 or whatever port we want to make a trunk. Mode on, because we set it to switch port mode trunk. We're not letting you negotiate anything. We are putting you as a trunk port, so you're always going to be on as a trunk. Then encapsulation 802.1q, because that's the protocol we use here. And then status trunking. So it's telling us it is actually trunking VLANs across. And then the VLANs allowed on trunk. These are the VLANs allowed, depending on what we configure. So this doesn't correspond to this, by the way. It's just a random show interface thing. So when you configure it on your own switch, run this command and compare and see if you could match up the commands that you put in there to this command. But this is how you read the data from your switch about the trunk port that you configure. So now let's discuss this native VLAN, right? So across every trunk link, we have a special VLAN configured called a native VLAN. By default, the native VLAN is 1 for trunk links. So that's why this 1 is 1 here. We didn't change it, so it's so 1. Any traffic that is untagged across the trunk is brought in on this native VLAN. And conversely, any traffic tagged using the native VLAN tag is sent untagged across the trunk. Trunks must agree on their native VLAN, which means both sides must have the same VLAN configured for the native VLAN. Otherwise, switches will throw errors. So this is how you configure it, right? You go config T, well, enable and config T, interface 024. So you go on the interface again, and then we put the switch port mode trunk, and then switch port trunk native VLAN 10. So this is the command, switch port trunk native VLAN and something. And then if you have a different native VLAN on both sides, you'll see this command come up. Native VLAN mismatch. Native VLAN mismatch discovered on this port. So you have to configure it as the same on both sides. So what I'm saying here is you have two switches, you have a trunk port between them, and we're going to have a bunch of these tagged traffic going across, right? So if you have VLAN 1, 2, 3, 4, 5, 6 on this side, your trunk could carry 1, 2, 3, 4, 5, 1, 1, 2, 3, 4, 5, 6. Or the same VLANs, right? And you're going to have this tagged traffic going across this trunk, because that's the whole point of a trunk, to carry across tagged traffic from different VLAN tags, and a bunch of them, right? So that's the trunk. That's carrying traffic for all these VLANs. But you're going to have this special tag that you're going to say, while the traffic is going across that link, it is going to be untagged. So for instance, this switch port trunk native VLAN 10 command, if traffic comes in on VLAN 10 on this side, we're going to strip off that tag and we're going to send it across this trunk without that VLAN 10 command. It's going to be just like a normal Ethernet frame, like we had a few classes ago before we talked about VLANs. So that's what they call an untagged frame. Just no VLAN awareness. It doesn't have that special 802.1q header. It's just normal Ethernet traffic. And then on the next side, the switch is going to take that traffic and tag it back with 10. So just across that trunk link is not going to have a tag, which is why both sides need to agree on this native VLAN, right? So that's the whole concept of a native VLAN. It's just one VLAN that you're picking out that you're going to strip. You're going to strip across the header, and you're going to pass it across your trunk without that header. And on the next side, you're going to add it back. That's it. So we can manually change the name Oops, I think somebody mute me there. You all Karen again, right? I think somebody mute me by mistake. Yeah. Just give me a thumbs up if you're hearing myself. I think I'll unmute myself. Cool, nice. So we can manually change the native VLAN of a trunk. Nice. Using the command switchboard trunk native VLAN something. So we just saw it was 10. Now we're gonna move on to the next topic now, which kind of related, as you'll see. So notice here, where it was, yeah, here, this native VLAN mismatch. You see the first part there, CDP. So CDP is what picked up on our native VLAN mismatch. So that's the next topic Cisco wants us to learn related to this whole VLAN madness. So layer 2 protocols, such as CDP or DTP, which is Dynamic Trunking Protocol, use this native VLAN to travel across switches. So that's the whole point of native VLANs, right? These layer 2 protocols utilize this native VLAN to kind of talk to other switches, which is why we need this native VLAN. Some other layer 2 protocols can also be used to help map out the network and figure out these inter-switch connections. We will be exploring these protocols more now. So 2.3 now, configuring layer 2 discovery protocols. So consider that you've just walked into a new data center or a new business or a new organization, and you've been tasked with drawing network diagrams of hundreds of switches and routers. What do? So, you walk into a data center, you see racks on racks of switches and routers and all of these things. And there's no documentation. Nobody has a network diagram of anything, which is a very common scenario. As you will see as you enter the field, nobody ever has network diagrams of anything. People installed it, and that was it. So you walked into a situation like this. And your first job or your first project is to draw network diagrams. So what do? Well, you could use several layer 2 discovery protocols to aid us in mapping out the network, which is just figuring out how the switches and routers are interconnected, right? That's what a map shows us. It shows us that switch 1 is connected to switch 2 is connected to switch 3. So 2 of these discovery protocols are the Cisco Discovery Protocol, which is CDP, and the Link Layer Discovery Protocol, LLDP. So CDP and LLDP, those are the 2 layer 2 discovery protocols that we're going to discuss now. So CDP is, as expected, supported on most or all Cisco devices. So Cisco Discovery Protocol supported on Cisco devices. Yeah. While LLDP is an RFC protocol used by other vendors. So when I say RFC, I'm talking about the standards, right? The IETF publishes these RFCs, and any vendor could implement these protocols. So LLDP could be used by a bunch of other vendors, and I'll actually show you a screenshot out of a Juniper device that I took. So using the show CDP neighbors command, we can easily map out our network without having to physically trace cables. So that's what we want to avoid, right? We don't want anybody having to crawl beneath data centers and following along fibers and with your hand, trying to figure out where every single cable on every single switch goes to. That's the last resort. You may have to do it in your life, but hopefully you don't. So to avoid that, we want to use these things, CDP and LLDP. So this show CDP neighbors command will give us something like this. So show CDP neighbor, again, not a config command. All our show commands are just here without the config part here. So make sure you exit out your config mode before you run any show command. So show CDP neighbor, you see your device ID, your local interface, your whole time is just telling you how long since you last saw that device, your capability. So you'll see the legend somewhere else, but the R here basically means router, S stands for switch. I can't remember what the I stands for. We'll see the legend in the next slide. And then your platform, so there's your device type, and then your port ID is the port on that device. So basically what we see in here is switch 1 is connected to R2, R3, switch 2, and switch 2. So switch 1 connected to R2, R3, and switch 2. Makes sense, right? Switch 1 is connected by 1 interface to R2 and 1 to R3, which is why we have 1 row here. So 1, 1, and then 2 interfaces connected to switch 2. 1, 2. Again, makes sense. We see in the diagram here. And and then the local interface. So this is the interface on switch 1 that connects to R2. So from switch 1 on port fast Ethernet 01 on switch 1, we are connected to fast Ethernet 00 on R2. And then on switch 1 again, on fast Ethernet 02 on switch 1, we are connected to Ethernet 0 on R3. So you see how we could form this map, right? If we didn't have, well, I can't really block it for you all, but if we didn't have this diagram below here, and we just ran the show CDP neighbors command, we could use this and create this map. We could just put, so from here, you just use this and drag out your symbols from Visio or draw.io or whatever you're using to map, and you create your names. So you put R2, R3, S2, and S2. Well, and then S1 we know from here. And then you use this local interface and this port ID here, and you start drawing links and labeling your links. And then if you want to know what type of device, you could get it from here. And then the technique here is after you connect out, well, after you map out everything from switch 1, you go to R2. So you SSH into R2, and you do the same thing there. You do a show CDP neighbors, and then from R2, you see everything R2 is connected to. And using this technique, you develop a complete map of your network. Yeah, so I hope you understand that technique. You just show CDP neighbors on everything, and you take a note of what devices your device is connected to, and draw it out in a small map, and then you map out the actual connections using this local interface and this port ID, and then you SSH into something else. So you can SSH into R2 or R3 or switch 2, and you repeat the process. You do a show CDP neighbors on that device now, you take a note of what it is connected to, and then you use the ports and you keep mapping out things and going until you reach the edge of the network. Yeah, so there's the technique here. Show CDP neighbors. Oh, yeah, look at the legend here. Nice. So you see this R? R is for router. T is for transbridge. B is for source route bridge. S is for switch. I is for IGMP. H is for host. These are just the capabilities. So these are giving you an idea of what the device is now, because that's what we want to find out. It's like, what is this device? I have no idea what it is. And the show CDP neighbors command kind of gives you a idea of what it is. So your technique is SSH into one device, show CDP neighbors, map out what it is. Go into this device, show CDP neighbors, map out what it is, and then keep going along the way like that. So most Cisco devices have CDP enabled by default. We can verify if CDP is enabled using the show CDP command. So show CDP, and it will tell you if CDP is enabled or not enabled. If CDP is not running, we can use the CDP run command to enable it. So you see we go into config T, config here, and then CDP run, and that's it. So we do CDP run, and we do our exit again, and then we go back here and do a show CDP command again. So you see before it was saying CDP is not enabled. Now that we do the CDP run, we could do our show CDP command, and we see this information here, which says we're sending CDP packets, and we're sending advertisements, which means CDP is running, right? So this is just a command to make sure CDP is enabled on your device, but most Cisco devices will have it enabled by default. Now, while Cisco devices have CDP enabled by default, many Cisco devices also support LLDP, but they have it disabled by default. So they support both CDP and LLDP, but they only have CDP enabled by default for a lot of Cisco devices. Therefore, the command LLDP run must thus be enabled to enable LLDP across the devices. Then you use the command show LLDP neighbors. You can run that and map it out on the network, or map out the network. So just as an example, show LLDP neighbors. Again, same type of information. So this is the legend here, and device ID, local interface, hold time again, capabilities, port ID. Same thing as CDP, right? Compare it here. Compare it here. Device ID, local interface, hold time capability, platform port ID. And this is show LLDP neighbors as opposed to show CDP neighbors. So again, we use this, we draw out our symbols, and then we draw our links and put the entry for each of the link. So we put a little text saying gigabit 02, 04, 05, and we draw out our map like this using LLDP now instead of CDP. So Cisco wanted to know both, right? Show CDP neighbors and show LLDP neighbors. So why do we need to use LLDP? Well, because LLDP is not a Cisco proprietary protocol, other vendor devices may support it as well. So this same show LLDP neighbors command, you could run it on a Juniper device, and you'll get local interface, well, parent interface and chassis ID and stuff, but you'll also get your port info on your local interface here. So you see, even though you all have never seen a Juniper device, you could use this and kind of map out those Juniper devices, because again, LLDP is an open standard. So other vendors can implement it as well, not just Cisco. Right, and now the last topic for today. So that was layer 2 discovery protocols. Now we're going to discuss Etherchannel or LACP. So these are all layer 2 protocols, right? That's what today was about, layer 2 protocols. VLANs, and then discovery protocols, CDP and LLDP, and now bonding protocols or Etherchannels. So now let's switch from a pure layer 2 networking field or discussion to discuss a larger concept called redundancy. In most modern day networks, some sort of redundancy is required at all levels. So redundancy simply means that we have extra or an excess of something. This includes having multiple links between critical nodes. So in everything in networking, you'll hear about redundancy, right? Redundancy means if you need one router to run a network, you put 2 or 4 or 3 or 4. If you need one link to carry traffic, you put 2 or 3. If you need one SFP to bring up a new link, you buy 2 or 3. Yeah. This includes having multiple links between critical core nodes, and this ensures that even if one link fails, and links can fail for a number of reasons, right? We just a few classes ago we discussed all of those interface errors that pop up, but we also have more realistic things like fiber breaks, connector issues, transceiver issues, a bunch of different things, especially if your fiber out in the open, strung up side the road. So this ensures that even if one link fails, connectivity is not broken because of the redundancy. So Etherchannel or LACP provides us with a way to create this redundancy by bundling multiple physical links into a single logical link. So what we're doing is instead of running one fiber between our 2 big routers, we're going to run 2 or 3 and use this LACP thing to let the routers think that those 3 fibers make up one big link instead of 3 individual links. Now, better yet, unlike other alternatives like spanning tree protocol, so we'll discuss spanning tree protocol in the next class. Unlike spanning tree protocol or STP, Etherchannel or LACP allows us to fully utilize all of our redundant links. So with spanning tree, you'll see if you put 2 fibers between 2 switches, spanning tree gonna run some magic and it's gonna pick one link between those 2 switches. It's gonna block traffic on the other link. With LACP now, what we do is those 2 links are treated as one link, as one logical link. So we can transmit traffic on both of those links. So Etherchannel, which is a Cisco proprietary term, allows us to group multiple redundant physical links into a single logical link, over which we can load balance traffic. This allows us to utilize all of our redundant links for additional bandwidth, providing both redundancy and higher speed links. So if we run 2 1 gig links as opposed to 1, we get 2 gigs of traffic, right? As opposed to here, where if we run 2 gigs here, 1 gig, we could only utilize that 1 gig. So Etherchannel typically allows a maximum of 8 physical links to be bundled into a single logical link. Note that all of the individual links must be configured for the same speeds and duplex configurations if they are to be put into an Etherchannel. So if you want to do an Etherchannel here, you can't have a 100 meg link and a gig link. It won't work. You have to have 2 1 gig links or 2 100 meg links or 2 10 gig links. Yeah. The simplest way to configure an Etherchannel is statically, so using static Etherchannel configuration. In this way, we manually configure our links on both sides of the group to form their channel groups. So that's what static means, right? We manually put in commands to form this Etherchannel. So we first select the interfaces that we want to be a part of the Etherchannel using the interface range command. Remember we used interface range before? Config T, interface range, FA01 to 2 or FA03 to 5. So we use that interface range interfaces command. That's the first command that we use. Remember that all of our interfaces must run at the same speeds. Again, it has to be all 1 gig speeds, all 10 gig links, or all fast Ethernet links. Can't mix and match. Then we put all of our interfaces into a new Etherchannel group using the channel group X mode on. So channel group 1, mode on, channel group 2, whatever number we're going to pick, just pick a number that's not being used already. And you just put channel group 1, mode on. So this is the first Ether channel we ever doing. You put channel group 1, mode on. Remember, we have to do this on both ends of the links. So these are the commands, right? So enable config T, interface range, gigabit Ethernet 01 to 2. So this means 01 and 02, right? You see both of them are gigabit Ethernet, so both of them are 1 gig links. Then we put channel group 1 mode on. So this mode on is the static bit I mentioned before. So when you see mode on, you're thinking static Ether channel configuration. Yeah? And then that's it. Once you do interface range and channel group 1 mode on, you just exit out. That's it. So that's on switch 1. You go on switch 2 and do the same thing. So interface range gigabit 01 to 2. And these numbers here don't need to match these numbers here, right? If you connect port 1 and 2 on one switch to port 3 and 4 on the next switch, you would replace this with the ports on the next switch. So you could do 01 to 2 here, and then 02 to 3 or 03 to 4 here. You just have to put the same channel group 1 mode on command. Channel group 1 mode on. And that tells it you are going to be an Ether channel. So that's Ether channel. We can also configure our Ether channel using the LACP protocol. So that was static Ether channel configuration. Now we're going to use LACP. Since LACP is not vendor specific, we can use it between Cisco switches and other vendor switches. Again, this is a big advantage of these open protocols. Instead of desirable and auto modes in other protocols, LACP uses active and passive. So you might, if you Google Ether channels anywhere, you might hear about desirable and auto. That's not LACP. That was another command that Cisco had in the last version of the exam for something called PAGP, which they removed in this syllabus. So in this syllabus, they just have static and LACP. So we just saw static, which was mode on there. That's all. For LACP, we're looking at active and passive. So a link configured in the active mode will continuously try to negotiate an LACP bond with its neighbor. A link configured in the passive mode will be open to negotiating an LACP bond if its neighbor proposes it, but it will not try to negotiate it itself. Therefore, at least one side must be configured in the active mode for a LACP bond to form. Alright, so kind of see it here whenever that thing goes away. What we think? Right, so interface range, fast Ethernet 010 to 11, channel group 2, mode active. And then interface range, channel 0 to 10, channel group 1, mode passive. So you could have one side active and one side passive if you want. You could have both sides active, but you can't have both sides passive because one side needs to start the connection at least. So, and then of course, after we configure our Ether channel configuration, we could verify our configuration using the show Ether channel summary command. So you just come in the same switch and do a show Ether channel summary. And you see there. So you can see what protocol it's using, whether it's static, whether it's LACP. You might see PAGP here if they're using that protocol that Cisco doesn't have in their syllabus anymore. And you can see the port channel. So you see we put up a port channel here, channel group, yeah, the channel group there. So channel group 1 is your port channel there. And the letters here are the letters here. So you see S, what is S? S is layer 2 and U is in use. So S and U. Just translate using this little legend here. So number of channel groups in use and number of aggregators. Then of course you see your ports that in this port channel. Yeah, so you can verify which ports you had put into a port channel before. You can verify which protocol is in use. This dash just means static, or LACP is LACP, obviously. And then you use these letters here and you translate it to this legend here, to these flags. Once we have configured our Ether channel using static aggregation, static configuration, PAGP or LACP, we can treat the logical link as we do any other and configure it with an IP address or whatever it is. Note that any configurations for the member ports of Ether channels are not applied. Only configurations on the bond are implemented. We therefore edit our port channel interfaces and configure them for layer 2 access or trunk ports or using no switch port command and configure them as layer 3 interfaces with IP addresses. So what I'm saying here is, let me say you have gigabit port 1 and port 2, right? You have gigabit port 1 and 2 and you run 2 fibers between gigabit port 1 and 2 on one switch and 1 and 2 on the other switch. You put them in a port channel with our interface range and then our channel group 1 mode on or active or passive. We put them in an Etherchannel. You don't just, so after you do that, you don't go under the interface. So you don't go interface gigabit 01 and put IP address 192.168.1.1 or switch port mode access. All of those commands that we know now. You don't go under that interface gigabit 01 anymore. What you do is you go under the port channel interface. So interface port channel 1 or interface port channel 12. Whatever we use to set it up, we go under that big aggregate interface now, and we put our configurations under that. So for instance, we could go interface port channel 12 and IP address 192.168.12.1. So instead of playing it under the smaller interface that we put into the Etherchannel, we go under the bigger aggregate interface and we put all our commands there. Yeah, same thing with layer 2. So for layer 3, we could put our IP address there. For layer 2, we could put it into switch port mode trunk or switch port mode access. But the important note here is that we don't go under the member interface, the smaller interface there. We go under the bigger interface. Yeah, and that's it. So in this class, we discussed a lot of layer 2 stuff. So we went through VLANs. So I introduced you to why we need VLANs, how to put it into access port, how to set up a data port and a voice port on the access ports. We discussed the default VLAN. We discussed what happens to connectivity when you put them in different VLANs, right? You can't ping between different VLANs by default. But when you set up inter-switch connectivity now, you set up these special trunk ports, and these trunk ports could go to layer 3 switches or routers for that special router on a switch configuration, and that allows us to route between different VLANs. And that is how we get back that connectivity between different VLANs. And then of course we have to use that 802.1q command to set up trunking. And you know why we have a native VLAN now, and how you change that native VLAN on different trunk ports. And then you have an idea of the layer 2 discovery protocols using that CDP and LLDP command, that you use to map out different things in the network. And then you know how to configure layer 2 and layer 3 Etherchannel using static and LACP. Yeah, so that was it today. We covered a lot of configurations, and all of the configurations, you should be able to practice them in the labs. So I tried to cover a lot of the theory in the class and a lot of the commands, but it'll really only start to stick when you go to the labs and you discuss, you do it for yourself in the labs. So if you're just floating around and you're feeling like you don't really understand anything and you just kind of lost from the topics, like it's just random words right now, go on to the labs and actually configure it. And once you configure it, you'll see it's starting to stick and it's starting to make sense in your head. Yeah. Any questions? Anything you want me to go over? Okay, well, not seen any questions. So take a break. Well, yeah, virtual break this time. Whoever is recording the call, I think you could stop the recording now. Yeah, because this will be the meat of the presentation stuff. And then once we come back, once you get some water and stuff, start lab 9, I believe. Let me see today. Yeah, lab 9. Which should be right CDP and LLDP, which is in the middle of what we do today. And let me know if you have any problems. Of course, lab 8 is also what we do today, so let me know if you had any problems with that one. And I hear so any call, message or take off your unmute your mic and ask me any questions you have. Yeah, so I'm gonna get some more today.